Hi everyone, my name is Ethan Vislosky. I'm a recent graduate from the University of Rochester, currently working at the Center for Astrophysics for the year, and will be starting my PhD at Johns Hopkins this fall. So today I'll be presenting my work with my advisor Regina Demina, as well as co-authors Zachary Brown and Edmund Chosedon, and our new method for constraining primordial non-Gaussianity will be looking at taking the moments of density perturbations. And we have a paper coming out along with this soon. Okay, so a quick overview of the theory behind this method. So for non-Gaussian initial conditions, the primordial gravitational potential can be described by this equation, defined phi ng. So phi in this equation, lowercase, is the Gaussian potential, and the FNL term represents this non-Gaussian deviations from the Gaussian potential, and we call this PNG. So the matter over density associated with this primordial potential is represented in this equation here, and in the presence of PNG, also known as a non-zero FNL here, um, introduces this bias B phi term, which relates the matter over density to the dark matter halo over density. And this acquires a scale dependent term, alpha, which is proportional to the wave number scale k squared. Thus, we expect to observe scale-dependent structures in the overdensity, which will be characterized by this FNL term. And a classic probe of this scale dependence is the two-point correlation function, which is just defined as the expectation of the product of these two fields. So the overdensity at some point x multiplied by the overdensity at some separation from that point s. So how do we detect PNG in our framework? So on the left here is a 2D schematic of how we evaluate the matter density field with Conquer, which was introduced by Zachary Brown. And essentially what we do is we compute two fields, the delta of x and delta of x plus s. And for discrete grids, this delta of x plus s is equivalent to just taking a spherical convolution at some scale s of the raw density field. So in this schematic on the left, you have W0 convolving it with a kernel of radius, say here 50 megaparsecs. You convolve it at each point across the grid, and the product of that is this field on the right, which sort of encodes the scale-dependent bias at that S value. So in our notation, delta of x is W0, delta of x plus s is W1. So we can just rewrite the 2 PCF in this formalism as the sort of the mean of the product of W0 and W1. So an extension of the 2 PCF or an alternative is to look at a series expansion of the moments. So again, the 2 PCF, the two-point correlation function, is the expectation value or the mean of the W0 and W1 grids. But the key insight of our method is that any Gaussian-like function can be approximated by a series expansion of its moments. So taking this raw product, W0, W1, we can get higher order moments, where the 2 PCF is just the first one, the mean, and then going to higher moments should give us more information when PNG is present. So we construct a vector, which is like our PNG estimator, and it is just defined as the product or the raw product of W0, W1. So this grid on the left with the one on the right, and it's normalized by the average random field correlation. Doing this normalization just allows for us to account for the integral constraint, or otherwise known as geometric effects from whatever your volume is. And again, this gives us a flat distribution here, or the flattened grids over spatial points gives us this distribution here at various scales. So for our model, we evaluate these distributions, as I showed in the previous slide, at various scales. So it's various radii of the kernel. And this essentially gives us a distribution sensitive to PNG at various scales. So we evaluate the field of three sets of 125 1 cubic gigaparsec dark matter halo boxes. These simulations were generated by Chassidon in 2023. And these three sets include FNL equals negative 25, 0, and 25 initial PNG conditions. So we can sort of compare these three catalogs to each other to get a feel for the scale-dependent bias as a function of FNL. So yeah, so just a note for future reference, the gammas, which we show here, are the average over all 125 simulations for each FNL case, and we get the uncertainties as the diagonal of the covariance from these. So here, this is simply just computing the moments from these distributions at each scale. So the first moment is just taking the mean at some scale s of our gamma estimators. The second moment is the variance, and the third is similar to kurtosis. Now we showed the first is like or is analogous to the 2 PCF. The second one, which is shown in the supplemental slides if you're interested, has primary non-Gaussian contributions from the collapsed trispectrum, and it also includes some Gaussian terms. And then the third moment has higher order correlations. So as predicted from theory, which we showed in the first slide, we see a pretty obvious scale dependence in the moments, and it's characterized by FNL. As you can see, the different FNL cases are non-degenerate, meaning that from this bottom panel, which shows the difference with the fiducial FNL equals 0 case with no PNG, the statistical noise represented by these shaded regions is pretty distinct. Even for the first moment, up to certain scales, you get some entanglement, but this should be characterized well by our covariance. So we construct a vector, mu hat, which is our observation met vector. And that is just the measurement of each of these moments concatenated into one long vector. So here we show how we model the FNL dependence of these moments. So in an earlier slide, we showed how the density field delta is analogous to our W0 grid, which is proportional to the primordial potential. So we infer from this that W0 must vary linearly with FNL. And therefore, we expect our PNG estimator, gamma, to vary quadratically because it has a product of these two grids. So we sort of write the formalism for the expectation vector here. It's just a simple quadratic with coefficients A, B, and C that can be fit given whatever simulation catalog you're using. So for example, here, using our FNL equals negative 25, 0, and 25 simulations, we compute the coefficients here. This is just like a simple interpolation. Now, just a note, obviously, we have 3 points and we're fitting to quadratic, so we're going to get a perfect fit. But what's interesting is when we take simulations which are kind of unknown to this interpolation because they exist at the FNL equals 12 mark. These are from the same general suite introduced by Chassidon previously, the dark matter halo simulations, but we don't use them to construct our expectations, so they're kind of unknown to the model. We plot those in red, so these are just the moments for the FNL equals 12 case measured from those simulations at different scales along with their error bars. And even for, say, 395 megaparsecs, where we get some deviation from the quadratic behavior, especially in the third moment, which makes sense because the third moment includes cube terms of our PNG estimator. Even though there's this deviation, it's well within the uncertainties or the error bars. So our covariance matrix should account for this when we probe out to higher scales. Yeah, so sort of the formalism that we test our model in is an MCMC framework. So we calculate a chi-squared, which is just the observation of our moments, so that concatenated vector of all three moments minus the expected vector, which is just that model we showed up here, the quadratic model for FNL dependence. And here the covariance matrix is computed from the 125 FNL equals 0 simulations. This is common practice to do for the non-PNG case. You get your covariance, and we show the correlation, the normalized covariance or the correlation matrix here. And again, this is a 54 by 54 matrix. So it's a bit coarse given our 125 sample size, but we'll discuss that more later. So the first test we do is on toy model data. So using our expectation vector, this mu tilde, we generate toy data for FNL equals -15, 0, and 15. And we get posterior distributions by minimizing the chi-squared for these three toy data sets. And this is sort of just a sanity check. It shows on the right here that we're able to recover the values of FNL that we seeded our model with pretty well, and that we get a relatively unbiased and sensitive result. Here we test the internal robustness of our model. So we do this by performing a pull test. This is calculated with this equation here, where we perform a pull for each FNL toy dataset by sampling 1,000 times from a multivariate normal distribution centered on the toy data vector and using the fiducial covariance. And then we measure FNL and sigma FNL for each of those 1,000 realizations. And the FNL in this equation, we do FNLi, that's for the realization, minus the expected of the toy model data. So you do this for each of the three cases, FNL equals 0, -15, and 15. And for a perfect working method, the pull test is expected to have a mean of 0 and a standard deviation of 1. And in each of these, we see this is very well replicated in our data. When we test on the -15, 0, and 15 toy data, we reproduce a, um, a perfect normal distribution for each of these cases with standard deviation of about 1 and no bias. So the more interesting thing is testing our model with a specific test case. So we use the FNL equals 12 simulations as a test case. And these are unknown to the expectation vector. So this test shows kind of how our model would perform in actual data. So we measure the observation vector for this simulation and minimize the chi-squared to find the posterior on the right here. And yeah, it reproduces or it retrieves the value of FNL close to what we'd expect. And this is very reasonable given our uncertainties. So we do another pull test, this case for the external robustness of our model. So here the FNLi is measured by excluding the ith simulation from our model slash covariance. And again, we have 125 FNL equals 12 simulations. So I goes from 1 to 125. And yeah, so we measure the FNL from each of those individual simulations and compute the pull from that. This gives, given that this is like a small sample size, only 125, especially considering our vector is has 54 bins in total, 18 for each of the moments. The somewhat higher standard deviation is reasonable. We also show in a later slide in the appendix that there is some ways to correct for this, at least comparatively. So overall, this is reasonable. We get about no bias in the mean and just a slight underestimation of uncertainties. So here we compare the individual moments. So we sample our test statistic with each individual moment as the observation. So just the first, second, third. And in doing this, we can compare the first moment or the 2 PCF to our model, to the second moment, etc., and different combinations. So our model is this mu1 plus mu2 plus mu3 in the cyan, and mu1 is like comparing it to the 2 PCF. So we see a 38% improvement in our constraint of FNL, and there's a reduced bias. So this is really promising results. And another interesting find that we saw was that the second moment is actually 7% more sensitive to FNL than the first moment. So, even not including the information of the 2 PCF, you can recover even more information with FNL. And there are some ideas of why this could be the case, which mainly has to do with the fact we're probing the collapsed trispectrum over a finite volume. But this is all exciting because it's the same computational load as just computing the 2 PCF, and you get all this more information. So here's just some plots showing the scale dependence. Um, more for reference, you can look at this and ask questions in one of the sessions, but just interesting that we see sigma of FNL, so our sensitivity is increasing, or in other words, our uncertainties decrease with scale, as we'd expect from probing PNG, which is characterized best at the larger scales by the scale-dependent bias. And again, another interesting find is looking at this plot on the left. For each of the individual moments, we see the second moment is a bit more stable across scales than the first moment. And yeah, so the next steps are primarily to test on larger samples, so a larger suite of mock simulations. And with improved stability from a smoother covariance with this larger sample, we can test things like expanding our vector using a finer scale step, larger scales. And the DESI volume will also expand our total volume that we can probe as it has general box lengths of 2.4 gigaparsec compared to R1. Again, and then our next step would also be to create a formalization for our method to be applied to galaxy tracers. So we can actually apply it to this DESI data. Because as for right now, we're just looking at dark matter halos, which are a more direct trace of the underlying distribution. And we're preparing a paper formalizing this. So thank you again, and I look forward to our discussions in the sessions.